All right. So, whoa, there we go. There we are. Welcome back. I'm gonna bring out Q. I'm telling you. Maybe I should bring out the Terminator. Be like, just. We'll just go from cute to like. Excuse me. Can we start, please? Sip it. Thank you. Thank you. Take it outside if you want to talk. This is being recorded. Thanks. All right. There. Sorry. See, if I didn't play cute, you get the ugly me. I got a lot to say. This is important to me. May not be important to you, but important to me. Okay. So, we're up to the part where we're like saying, hey, a sum score is full of stuff. This is why it's a hot dog. Right? What do you think of this list? Disagree? Think there's stuff I left off? What would I leave off? How about what else? Oh, yeah, possible. Yeah, that's what I think too. I'm like, hey, what did I leave out? I just want to quantify. Like, I feel like I would read this stuff, especially in the SEM world. Every time you make a method, you have to sort of pitch to get it to be used. I didn't make SEM, and I don't make SEM. That's fine. But I read the textbooks, and it's always like, oh, measurement error is a problem. Measurement error is a problem. Measurement error is a problem. Yes, it is, but there's a lot of other problems too. And SEM still has its problem with a number of these. So I'm going to try to get into those as well. This next step. But other, huh?
And it may be, I don't know if, I don't have enough of a background in it, but I don't know if theoretical error is the same as measurement error.
Yeah, it could be. Theoretical error basically being, your construct isn't quite the construct. Yeah, I think that actually I probably would lump it in here. You know, like if T is not really well defined, that's going to happen. It's hard to tell when you add things together because how do you know, what do you know about model fit? Is there model fit in a sum score? No, right? But there will be in just a moment. But no, generally no, there's not. So, anyway, this is my sources of error. I'm going to bring this slide back in just a moment about factor scores. They're not a whole lot better. They take care of a few of these things. But anyway, so why does error matter? Error matters because it might cause, I'll put might. It's not guaranteed that error will always lead to this. It's possible that you'd find the same result even with everything the way you want to, but just know that you wouldn't know in the first place. But if you do use just a test score and analysis, you're like 99.9% of all other studies in the world, so you've got company. But it could lead to biased results, right? You could have biased estimates. So like if you put a score into a regression model, then what you can do afterwards is that beta weight in the regression model is going to be closer to zero. It's biased downwards. It's less strong. So if it's less strong, you're less likely to think there's a significant effect there, which is a type 2 error, right? Failing to reject a hypothesis when you should. Competing against this, though, is the standard errors of estimates. So standard errors are involved in figuring out the denominator of a test statistic, right? And so if they get really small, get small, the test statistic goes really big. So even if it's not significant, you're more likely to make an error, a type 1 error, than standard errors. And in the history of statistics, type 1 error rates, this is not just psychometrics, but just statistics at large, type 1 error rates are the devil. They're terrible, right? You don't want to think something is there when it's not. They're much more egregious. But in like the SEM setup for what we do, it's like, oh, measurement error is the problem. You're getting all these you're losing power. And I think really some of the problems, not just measurement error, but some of the other problems lead to type 1 error, which is really bad. So now type 1 error gets into, there's been a recent debate about replicability of research results, particularly in social sciences. I don't know if you heard about this recently, but if you read certain journal articles and certain other National Academy of Sciences, proceedings of the National Academy of Sciences, it's been very concerning that a lot of the social science research that's out there is not replicable. So people will try to replicate studies and not find the same results. And these are results that were used using these types of methods, and I think part of that is the type 1 error issue. Now I can't connect the two. It's correlational right here. This is not causational right now. I can't go in. I don't have any evidence to suggest it, but anywhere that you have type 1 error, it's a case where you have non-replicability possibly, because there's no effect to be found, right? How can you reproduce a effect that didn't get found? Oh, only error. So 5% of the time you might be able to, right? Anyway, so it may not hurt you to use a test score, but it might, and that's the problem. And in science, we're trying to go and use the best methods that we can. So in terms of what error hurts the most, some source of the error on the previous slide matter more than others. And in just, if you read just the SEM texts, a lot of the ones that I assigned for this class, and it may not have been in the chapters that they assigned, but usually in the intro chapter or the conclusion, measurement error is made out to be the thing that's the worst. I actually think it's not measurement error that's the problem as much as we think it is. It's actually all the model misspecification error that causes the issues, right? Because model misspecification error could be much more egregious. Remember the result last time where we took the SOG, we were predicting the gambling factor from the SOGs, and we had to go and tweak the model a little bit because one of the items had differences in people on the variable. Right? Our results didn't change, the p-values, we still have made the same conclusion, but the effect size changed. And so that's, I think, kind of a case in point. We saw the same thing. We saw the estimate get downward. Actually, no, the estimate was, the misspecification error made the estimate stronger, but we saw the standard error get narrowed. And so we had all sorts of issues in that case. So I do think model misspecification error of all 5 types, even including some that we can't really do with methods I've taught you in this class or assess with methods I've taught you in this class, is a bigger threat to the validity of your study and the accuracy of your results than measurement error. But that being said, measurement error is actually the easiest to remedy. So, do you have any experience or thoughts on that? I want this to be a discussion also. Yeah, Hong Lei.
The model's misspecification error is pretty self-explanatory.
Mhm.
How about the measurement error? And could you please clarify it a little bit?
Measurement error is in the idea that whenever you assess somebody with a psychometric instrument, there's some error due to measurement itself. And we quantify measurement error if we're just using a sum score. It's quantified using, usually it's the standard error of measurement, which is the reliability times the standard deviation of the test score. That is how much error there is. So it's related to reliability. The less reliability there is, the more measurement error there is.
So basically, it's just error by using this specific standard.
That's right. Reliability is supposed to be an index of how close to precise your instrument is. The bigger the reliability is, if reliability is 1, for instance, there's absolutely no measurement error. Actually, pardon me, this is 1 minus reliability. All right, so if it's 1, the standard error, oh, no, never mind. Never mind. No, this is it right here. Pardon me, I get this wrong. Standard error of measurement, folks, help me out here, classical test theory. I'm shooting myself in the foot.
I think it's 1 minus.
Is it 1 minus? Yeah.
If you have perfect reliability, it'd be
0.
That's right, it'd be 0 error. Thank you very much. Thank you. Yeah, that's, pardon me. I knew there was something wrong. Thank you, Jake. Sorry, I don't think in classical test theory units as much anymore. I'm on the factor score side more often than not. Anyway, no wonder I'm telling you the message of we should never teach classical test theory. We really shouldn't. But let's go on. So that's center of or what error really is quantified as usually. But conceptually, it's essentially what are all the things that go on when someone takes a test that may cause their score to wiggle a little bit. Right? Fatigue. Lack of understanding of items, misspecification of the factor or the trait itself, miswording of items. I mean, there's all sorts of stuff that contribute to measurement error. And in a classical tester, when you just take scores of items and add them together, they just all get compounded into one tight little bundle, and we try to assess it by figuring out a reliability.
Then is it person specific or scale specific?
It could be a little bit of both. It's idiosyncratic, yeah. Mm-hmm. Scale specific would show up across all people, although generally speaking, it's an interaction between scale and person, right? So I'm really hard to communicate with. I've come to understand, and So therefore, when I read an item, I may take it very differently than most people would, right? So like I didn't understand how this was worded, but that's just me, right? So
Because it's just only one single score.
that's it.
The whole test.
That's right. You can't tell anything more than that, right? We've just taken every number and added it together. Aggregate data.
And is it separate? But because just now you were saying
Mhm.
that is, all the like the wording or even is it completely separate from the model the specification or just?
It depends. If you misspecify your model in some of the ways, if you can actually provide a model for this, and when we get to the CFA analog of classical test there, we'll see it, then some of this misspecification will show up in the CFA analog of measurement error. Yes, but not all of it. So, and they do get related, yes. Devane.
That outcome distribution misclassification error.
Yeah.
Is that in spite of the line of research that says that at a certain point with liquor type items you can assume they're continuous?
Absolutely. I'll show that you can't. But that's fine. Yeah, there's always an error with that. It's like what's close enough, but their metric of what's close enough is using things that are also having error in it. It's not really made it. But yes, absolutely. There's not really, the line of research is there, and they always come to the same conclusion, but that never fits the data that we have, usually, I feel like. So, and actually, I'll just tell you right there, that tells you, like CFA, this draws into to question pretty much everything we've ever done in this class in CFA, because everything's a Likert item, right? I actually know, in looking at a lot of the research that's been done to compare it, what ends up happening is that they confound this source of error with some other source of error. And so it's tough to disentangle which source of error is causing more of the problem. So I think in the common thought process, I've taught this class with the way people do it, and then the way people do it is CFA, and it's a lot easier to use CFA than to go outside of it. But Billy Skrupski and my wife would both tell you IRT or somebody like treat Likert data as categorical anytime that you can. And I agree with them. It's just really hard to do, right? It's hard to get an estimate of things to work. If you have 6-point Likert scales and 95 people that took your test, you're going to have some items that people didn't circle a 5 or whatever that would be for. So how do you fix that? What do you do with it? And it takes a lot more effort. So, but yeah, that's exactly it. So, kind of going on the tangent here, but yes, that's it. There is a lot of research that say when it's okay, but again, every time I read a study, and I don't have a specific example apart from it, but I find that I feel it's confounding other sources of error in the study, and I can't tell you how much that is outcome distribution versus how much it is otherwise. I was actually trying to build a simulation study to put in this class to show you, but I ended up not being able to get it all done, so I'm sorry. Next time. Other questions? I like the discussion, by the way. This is awesome. I want this to become, like I can sit up here, and in a few slides it's going to get technical because there's a thing after you all, our students went to NCME this year. I read a few things and I'm like, boy, the field needs some help. The field needs better instruction in grad school, and that's what I'm here to do. So, anyway, here's one thing I want to tell you. This is a slide that Lisa and I kicked this around for years. Your GRE score. Let me just start out by saying, I have never used a GRE score in admissions decisions in my life, and this is part of the reason why. There is a book that you can read called The Guide to the Use of Test Scores of the GRE. It's at that webpage right there. And if you take the 2011 guide, it provides for you the conditional standard error of measurement. Now, mind you, this actually isn't correct. This is the number they want you to see, but the properties of statistics don't work this way. The further away you get from the middle of a test, more often than not, you see bigger error and not less. And that's because they put a scale limit to either side, and they come up with this number based on simulation to actually do results from research on this. But this is your GRE. This is the old scale. This is 2011. The conditional standard of error of measurement ranged from a version of 9, which I believe is right up here at the top of the scale, to 55, which was right here in the middle. So what does that mean? if you had a GRE score of 500, if we go and build out where your true score might be, if we put a confidence interval around it, plus or minus 1.96, if you will, if we think of it as normal and you take enough items on there for it to be normal, your true GRE score should be somewhere between 400 and 600 on average. Whoa, right? How's that make you feel? I talk about this in a lot of classes, but this is the problem with it, right? This is huge. This window, did you see this? Have you seen this window before? The truth of the matter is, again, this is generic. Each one of your GRE scores has a very specific standard error of measurement to it because of the items that you took, and it's not going to be the same for this. So this isn't even accurate, and this is what they're telling you about it, right? So when I look at this, I think I can't use this test. Now, the new version of the test did a few things to make this a little bit better, but I still don't particularly agree with it. But this is why error matters, right? Knowing about what goes into it. Sorry, I see some frowns.
How is it so crappy?
Yeah, that's it.
Is my question.
This is where we need better training, because when you get into the field, you're going to be the people who stop this. All right, it's not me. So there's no way in hell I'm going to work in the field. But I'm going to train you to do better at it. And if you're not in the measurement program, I'm going to train you to expect more from measurement when you do work with it. That's what I want you to do. That's the only thing I can do. I can't fix everything, but I can try to give you my perspective, and I can also try to back it up with trying to give you every evidence I can. And this is where I'm saying, if you can criticize this, please do. I presented this slide, or a version of it, at a workshop in Nebraska in 2009 with Kurt Geisinger in the audience. I quoted the 55, and he was so offended by it that he sent an email around to his colleagues and students about it, that I had several friends that had sent it to me. That it's just terribly inaccurate information. It's like, go find the PDF. It's in the back. It's published. Right? This is them. Right? So it's like, we use tests all the time, but we forget error. Right? So this is where error matters. I was sitting on when I was dating Lisa, I travel out to Nebraska and then go back to Athens. And to get to Athens, there's a shuttle from Atlanta. And, it's long enough where you can strike up a conversation with someone. So I was sitting there, and there was a woman who was an applicant interviewing for counseling psychology doctoral program. And she mentioned her GRE experience and whatnot. And I said, well, I did psychometrics, like the GRE. Oh, yeah. So one time I took it, and I got a 600. Sorry, one time I took it, and I got 400. And the next time I took it, I got 600. I improved that much. And I did not say it, and I'm like, that's entirely plausible with numbers like this, right? So think about what you do to get into grad school. You keep taking a test and taking a test. All you're doing is you've got this distribution. Sorry, I won't go on Huey's. I won't paint his. Right, but this is where the admission standard is. All right, here's your odds of making it above that, right? You could go and predict how much money you'd have to spend on the GRE taking it multiple times just to hit that, just by error of measurement alone. Isn't that nuts? And you REM students, we want to test you for your comps. I'm not going to back down. Anyway. So GRE, though, is a factor score, and it's a good segue why error matters. And I just wanted to say that here because I'm not going to tell you that factor scores potentially are that much better, but I want you to understand them a little bit too, because they show up from time to time. And I will say this, factor scores are not the work of the devil, even if you use measurement models. The GRE's measurement model is an item response model. Just because you put a fancy label on it doesn't make a difference. Factor scores, though, come about it in certain forms, and that's where I want you to understand the forms of factor scores, what types they are and how we summarize them, and what we have to believe to use them themselves. So, okay. So remember what a factor score is? It's F. Here's our CFA model for an item up at the top here. We have an item Y. Here is F. This is a CFA model, but I'm conflating this with IRT as well because the methodology is the same. What I'm about to tell you here, bless you, is the same regardless of whether it's CFA or IRT or whatever else. It transcends. Once you put a distributional assumption in that locks it into a specific score, but the concept's still the same. So factor score is an estimated value. All right, it's like we try to figure out F. And there's been a long resistance to using factor scores in psychological research, and I've seen oftentimes it's said that factor scores are indeterminate. Have you heard that before? Indeterminate. Can't figure them out. Indeterminate. And there are ways that people will talk about what indeterminacy means. The definition I quite like a lot is that whenever you realize to come up with the factor model, we had to make certain assumptions about the factor. Right? We had to go and identify the model. Usually we fix in this class, we fixed the mean to 0 and estimated the variance by putting a marker item. Right? Had we done a standardized factor, guess what? All right, so let's imagine we make a factor score using the methods I'm about to show you. And we had a marker item. And we make a factor score using the methods I showed you. And we have a standardized factor. Are the factor scores the same? No. And that's, to me, what people say when they talk about indeterminate. They're not the same, but what is the same is the rank order of the people and the magnitude of the difference. So that rescaling that we're doing, even though the number is changing, it's an interval scale. It's an interval. Well, it's supposed to be it's not an interval scale entirely. I'm going to get to that. It's supposed to be an interval scale. If everything works perfectly and we have no measurement errors, an interval scale. But even then, we can just change the numbers, and the scale is still the same. It's just change the location, right? Change the variance. So we do this all the time with test scores anyway. We change, convert a 12 into some number that's around 100 or something like that. Right? So factor scores themselves. Here's your depiction of these estimates, and this is a latent trait score. I would like your opinion as. I'm not going to tell you what trait this is. We're going to play a game here. We're going to play Pick the Trait. And on here we've got a person, we'll call her Taylor. She's up here. These are slides I borrowed from a job talk I gave here at this university. And then here's Miley Cyrus. And her score is over here. And then we got Justin Bieber. So if you were to pick this trait, which trait would you call it? What's that? What a terrible scale, right? Some of you might want to say singing ability, but then you'd have to say that Taylor Swift and Miley Cyrus are on the high side. I have to admit, I like Taylor Swift quite a bit. I did not get tickets to her conference. That would be creepy. That is one that I don't go to without my daughter, who's 8. Actually, I don't go to, period. Never mind. Who am I kidding myself? If there's not a mosh pit, I'm not going. If someone's not going out on the stretcher, I won't go to the conference. Or the conference. Also the conference. The problem with NCME is there has been not enough violence. Anyway, so the latent trait, by the way, was given to me by my daughter, Daphne. There she is right there. And then she said that is their ability on math scores, Dad, because everybody knows girls are better at math than boys. So I thought that was pretty awesome. I had to put that up there. But this is trying to prove a point. That's what we're trying to do. We have this continuum of scores. Right? It goes from high to low. I don't have a number on here because the numbers are relatively meaningless. But what comes along with this, though, is the factor score itself is providing what's called a weak ordering of people. If you're those of you in the measurement program, anybody can, but the measurement program may be more inclined to. In the 1960s, there was a series of papers and neat stuff that came out under the heading of axiomatic measurement. So it was a series of mathematical stipulations as to what made for an interval scale itself. Clyde Coombs at Michigan was somebody who did this. A number of people at Michigan that did, and it's a very strict definition for it. But one of the definitions I'm using here is that what a weak order happens to be, which means we may know, for instance, that Taylor Swift has more math ability than Justin Bieber. Right, so she is greater than Bieber, but we don't know, for instance, whether or not she's better than Miley Cyrus. All right. So we have an order for the most part, but there's some places in the order where we can't determine. Right? And that happens when we consider that each factor score, or the latent trait score itself, really is supposed to represent, when we add error to it, kind of the most likely or average of a whole possible range of scores of one of these people. So this is my weak attempt at overlaying graphics on here. I'm sorry for the quality. It's a little fuzzy here. I did not redraw our graphics last night. Sorry. right? But so Justin Bieber down here, yes, he's got a nice range to him, but for instance, we can't tell if Miley Cyrus or Taylor Swift is bigger than is better than each other, right? If we were to say, what's the probability that Taylor Swift's score is greater than Miley Cyrus's, we'd have to go and take the probability, figure out where these distributions overlap. We could do it. These are distributions. We could find it, right? Better yet, here's one for you. Take the graduate admissions criteria for GRE scores and say, what's the probability you really are bigger than it or less than it when you get into grad school, right, for each one of your people. And this is one of the things the GRE guide does do well. I will put it there, that the GRE is not meant to compare people right beside each other. Right? If you had somebody in the old scale who was a 600 and someone who was a 610, you can't say definitively that a 610 was bigger, and that's what this old scale said. The old guide said that. And in fact, that was some of the reasons given when they switched the scale from the metric of 200 to 800 to the new metric, which is 130 to 170, is it? So it's to emphasize that the scores are really not that far apart from each other when they're right next to each other, and that's part of the reason. You've got this error, this overlap, so that's a good thing. I'm trying to pay compliments where it is, right? So this is the idea of a weak error. If we didn't have measurement error, however, those are little distributions right there, we'd be a lot more certain. And in fact, we would have this, if the model fit well and we had no measurement error, we'd have this perfect, nice, the weak order would go away, we'd have this interval scale, we'd be happy about it, right? And this didn't matter if we used a marker item or a standardized factor or whatever, we'd still get this ordering of people out of it. So, does this jive with your idea of what we're doing in psychometrics? Jive. Old language. Yeah. Speaking of jive, it makes me think of the movie Airplane. And Kareem Abdul-Jabbar was the pilot once. And once I was sitting right in front of him in first class on an airplane. Isn't that funny? And I thought of all the airplane jokes I could say, to turn around behind him, just like whatever. And I thought, no, dude, just leave the guy alone. I wouldn't want to be him and have me in front of him. How many times has he heard that? Anyway. So here's a set of example factor scores, draw, Templin, draw, and their distributions. So factor scores represent the idea of a distribution. And if we were to think about this concept that we started with classical test theory, we started with the idea of saying that, a person, if we were to give them a test and then wipe their memory clean and give them another test, we'd see this fluctuation in their score. That's the distribution of their score. Now on the factor side, the similar concept to it. Right? So the different version of the factor model identification would change the numbers down here. Right? So these would no longer be -1 to 4. Maybe this would be, negative. Maybe this would be a number of -0.5 or something like this, and this up here would be a 1. Right? But the pictures themselves wouldn't change themselves. The ordering of it. It's all relative. Right? Okay. So the factor scores that I just pulled up. This is from this is a lecture I built when I was in Georgia. And I used the gambling tendency, used the GRI again, and I just built these factor scores trying to get this point across. It's it's CFA, that's factor scores. But the methods I used for it to build those factor scores are the same methods we use to build the GRE score that you got. And that's what I want to talk about right now. And the only difference in the methods is that in CFA, I'm assuming normal items with a normal factor, and in the IRT model for your GRE, you're assuming items that are Bernoulli distributed or multinomial with 2 categories and normal factors. But then you put it into you put the distributions and you to this general form. So they behave the same. And so one thing I want to tell you, this is where I'm finding my motivation in odd spots. I'm sort of always been an anti-establishment person, and I don't ever want to be. Evidently, that's just going to keep me from being ever the establishment, and I'm okay with that, right? So that's fine. But here is a part from it. I found a set of slides here. There was a colleague of ours, a person by the name of Walter Stroop. Believe it or not, I know 2 Walter Stroops in the world, and they're both in academics. One of them works at Nebraska. And he's a statistician, and I'm using his book to teach the class next semester. He's awesome. I'm looking forward to that. The other one is at the University of Texas in Austin and does, I don't know if it's educational policy or fairness or something like that. And he showed up at a conference on test security or test sensitivity a couple of years ago here on campus. But then I found a Mother Jones article on this guy. So if you Google Mother Jones and Walter Stroop, you'll find that he has run afoul with one of the biggest testing companies in the world, Pearson. Those of you who went to NCME, did you go to Pearson? Pearson events? See any Pearson people? Yeah, they're not the problem. I mean, not everybody's the problem, but so somehow, and this article did a great job of describing it, and it's sort of, you know how journalism is. It's trying to tell a story to get you to read it rather than laying it out. My perspective on it might be a little bit different. I do think that the premise of the article is true. Some of the execution may be less causal than it's suggested. But essentially, he said to the Texas legislature that the tests that Pearson's giving in Texas aren't valid for doing what they think they're doing. And Pearson took exception to it. And in part of the response of Pearson to this guy, they went at length. Evidently, Pearson has a position where they fund a lot of the REMS students or the analog of REMS students at the University of Texas. Right? So those of you in my program, you could be getting scholarships from Pearson to do grad school. And it's a great thing. Right? Because then they go and get the internships at Pearson, and they work in the industry and so forth. And the University of Texas, according to the Mother Jones article, had said that, I believe it was Mother Jones, I hope it was, maybe I'm wrong about that, had said that, hey, look, quit threatening our relationship with Pearson. So he had people attacking him from Texas, and then he had Pearson attacking him overall. And here is one of the responses from Pearson, the biggest, I want to say the biggest testing organization. I remember reading the bottom line of Pearson 2 years ago was $9 billion in profits, right? This is what they say. IRT does not rank order students or select test questions. Now, hold on a second here. The scores that you get don't give you a rank order. But let's go further. Help me pick out the problems with this. IRT simply measures students' academic and knowledge and skills on a scale like a ruler. Anybody? Problem? Let's back up here. First of all, if we let them say ruler, doesn't a ruler also provide a rank order of students? Couldn't we rank order each other by height? More bars in more places, right? Right? Just height. We can stand from highest to lowest. Remember the ruler comment. But second of all, let's go with a little bit of an axiomatic measurement, or even not have axiomatic measurement. Let's go with introductory statistics. What level of measurement does a ruler provide measures on? A ratio scale. There's a fixed 0. What level of measurement is a factor scale on? At best, an interval scale. More likely, an ordinal scale, because there's ordinality that happens in the change of factor score. Right? This is from somebody telling the state of Texas, no, our tests are good, this guy's a quack, and here's why. And this right here has fired me up so that you students in my program, when you get out of here, if you put something else out like this, I'm going to be disappointed. I told you better. Right, don't do that. Come on, you hurt all of us as a field when you put out garbage like this, right? It just doesn't help. So, anyway, it gets worse. I could go through each of the other things, test scores and growth and everything. Don't get me started on growth. So let me say one thing about growth. I mean, did any of you go to any sessions on growth at NCME or AERA, growth modeling of students? We spend a lot of items to pin down precisely a person's factor score of ability. And yet we talk about putting it into an analysis model where we're going to measure growth on 2 or 3 occasions. How precise is our measurement of growth then? What is our reliability for the growth estimate with 2 or 3? It is like assessing ability, not quite, but almost like assessing ability with a 3-item test. That doesn't seem to get talked about much in growth modeling, but it's all part and parcel with this right here. Talked about. So anyway, you can read the document from Pearson Assessments online, the PDF response to them. You could read the Mother Jones article. It's a very interesting world that we live in. And in the educational measurement world, we don't suffer from the problems that you have in psychological measurement, where we have so much data we don't know what to do with. But then we have just as bad methodology from people who are by and large trained in the field to be able to do this. So now my pledge to you, the students, I'm only talking to my students in my program, I will not let you out of here until you get this, all right? And if you go to one of those programs, testing companies, I'm not going to say anything about it. That's your career choice. It's a good career. But do the best you can to the truth, and we'll all do better. All right? Don't hurt us. Anyway, so more on factor scores. Factor scores, sorry, any thoughts on this? Let me ask you. What do you think of this commentary right here?
I always have some thoughts.
Thank you, Julie. I want to hear, this is more, I don't want this.
I know very little, but I have.
No, not at all. Stop that.
One of the things I think about is the testing that goes on in schools and how my kids are in middle school and they are so driven by these tests, and the kids are primed at the start of the semester, and they were kind of dinged last year because they individually have these like scores that they need to try to make improve by the end of the years on these tests that I suspect are very similar to this.
Absolutely, yes.
And so if they only got an increase of 2, I'm thinking,
where's that on
the
this curve,
teachers
right?
are
Yeah.
not, I bet they're not understanding that they're well within the
Oh, that's exactly it. Yeah.
But if they go down a little bit, the kids they don't get the pizza party.
That's ridiculous. And the teacher themselves also get in trouble potentially.
Yeah. And my kids came home from school. Like one of them was really bummed out because her score stayed the same over the year. I mean, she scored really high at the beginning, and she's like, some people are now starting to purposely do bad on the early score.
Yeah, gaming the
So now
test.
we're,
Yeah.
all messed up with her.
So where does the teaching happen with all this is what I want to say too. Yeah, that's another issue. So it's exactly. That's it exactly. We've got so much money. And not only that, there's so much at stake with this now because of the way that we've done it. And I'm not saying that we can't have a happy medium, but we get so little out of the tests. Pizza money and stressing about tests rather than worrying about the subject area.
Well, and it makes me think about the effects of how it adjusts other psychometric tests that these kids are then taking.
Oh yeah.
After
Your self-concept of your ability to do whatever.
Yeah. So it's kind of compounds everything.
No, I get it. I'm frustrated with it too. It's an interesting world. I think that we have lots and lots of tests out there in the ed psych side or the educational measurement side that are purportedly to assess how well our teachers are doing, and yet they're getting in the way of letting their teachers do their job in the first place. Anyway, we can go on for that. Believe me, that we'd be happy to talk about it later more. But let me go back to the research side. Sorry, this is for those of you REM students in here. I want to get this into your head a little bit because sometimes I feel like nobody else in the program says these things. Nobody in the center, nobody in the program, nobody else. Let me be the voice of contrarian and say what the hell. So anyway, and then they can come attack me and whatnot, and that's fine. Whatever. I got enough meat on my bones right now to last a while if I can't pay for food, so I'm good. Maybe some of you can spare me beer money or pawn my award for some beer money. So factor scores or things by other names get used in many domains, right? We don't call them factor scores in IRT. We call it ability, or we call it latent trait estimate, or we call it theta. But it's used in the same way. Believe it or not, well, I'll get to it in just a second. Remind me down here. I'm going to put a little note down here. Down here. One of the problems with factor scores that I perceive why it's gotten so notoriously bad in psychological science is that there's been a really weird relationship of EFA, exploratory factor analysis, kind of confounding things as we go forward. And the problem with EFA is if you're trying to do an exploratory factor analysis, now you already know I hate it. There's not a concept already, and I'll take multivariate and I'll tell you exactly why. I decided that we don't have time for this semester. But if you don't know what's going in, how do you use a score to signify what you don't know happens, right? I think that's one of the bigger problems with it. Right, with a CFA, you're supposed to know more, and you can build the model and look at the score, and then you have a little bit better sense of what the score is supposed to represent. So that's one of the problems. The other problem is that since the 1930s, there have been and I put the word crazy methods for determining factor scores, many of which were developed in the EFA days because we didn't have good knowledge of statistics and didn't have good access to computers. but a lot of those are still in use. There's a nice paper that's been published, but it's also on the NIH website that talks about all the different methods of factor scores. This is by a person named Michael Neal. He's one of those elite 65 at the table people. But it was a nice way of putting things together. I will note the formula that I'm about to use, and his had a problem with the where the transpose was. It doesn't give you an exact matrix product. I just to put it out there to you. Not a knock on him. I've made typos before. Heck, my book has a heck of an errata list online. Isn't that right, Online? She found an error in it today. So anyway, not trying to point fingers. Just a note. A lot of good stuff in there, though. What we're going to focus on today are the methods for estimating factor scores that are used in pretty much every field that uses scores. Used in wide scale in educational measurement industry. But the thing is, we can do it in CFA as well. And in fact, if you ask Levon to do it, or ask M+ to do it, or any program, well, I don't know about the other programs, but Levon and M+ certainly use this method, so we're good. This method also is in use in other fields, such as mixed models, so multi-level models. In multi-level models, people use multi-level models because of the same problem. If you're looking for, let's say, differences in classroom effects, without a multi-level model, you'd have to go fit a regression model for each classroom and then take all the beta weights and put it in another model. And we have this propagation of error problem. So in the multi-level model, it says it essentially gives a theta for each unit at the level of the classroom, or a factor score for it. And that factor score goes by the name of the best linear unbiased predictor, or the word, Megan? BLUP. So it's an interesting world. To the statisticians, BLUPs are nuisance parameters, right? Your factor score, to us, it's everything. To them, it's a nuisance. And the thought that I've had a few, when I taught at Nebraska, it was great. I had some of Walt's students in my class. And the other Walt Stroop, the one not persecuted by Pearson, his students were like, factor score is a BLUP? Who would ever use a BLUP? Like, it was just like this, it's like, really? And I'm like, well, realize the whole design of it is to estimate it better, and so it's not a problem to use a BLUP. It's just more, the method, I'm trying to say the methodology is the same. It transcends. It's based on things that are above just the specific of the model. So the big picture is the factor score is the estimate of a subject's unobserved latent trait. Because the latent variable is not measured directly, it acts like missing data, right? You really don't know with certainty its true value. It can be anywhere on there, right? Your children, Julie, didn't quite get their 2, but even if they would have gotten a 2, they may not have actually, that was likely. How much more likely than that, the 1 or whatever? Is it possible? So it's different to pin down what the missing data value happens to be. Therefore, the use of the factor scores or the sum score, if we're going to use these later on, we have to reflect that error. And that's what we're going to get to, looks like, next week. And certainly we may get to some of these slides next week, too. Anyway, this is really important, though. Critically important. So there's our scores again. So this is the distribution of factor scores. And these are all normal distributions, and that's not a coincidence. In CFA, I'm about to prove to you, using statistics, factor scores are normal. They are. Right? Our best guess. Factor score distributions are normal. Now, that doesn't mean sources of error that we talk about might corrode what the truth is, but the factor score distributions are normal in CFA. In reality, they can be anything. So here in the bottom here, these distributions are called posterior distributions. Have you heard that term before? Where have you heard that term used before? Bayesian, right? So, oh no, Bayesian's the devil too, right? Our CFA model, when we made that assumption about the factor being normal, that was a Bayesian model. Don't tell anybody, right? Anyway, we're taking the posterior distribution. That posterior distribution has a shape. So when I said before there is no score, there's just a distribution, right? The question then comes, how do you figure out what a score should be? In a normal model, it's pretty simple, right? With distributions, we could pick the peak. That's the maximum, like if we're using maximum likelihood, right? Wherever the point of the top is, that is one score. And in a normal model, that's one version. We could also use the mean of the distribution as a summary statistic that would represent a score. Right? Both of those have different names and meanings in the terminology. If we were to summarize the distribution with its mean, the word of that is something called expected a posteriori, or EAP. It's the mean of this distribution that we're summarizing it. Right? So your score on the GRE, I believe, is an EAP score. It was the mean of all of the distribution of all of your factor scores that possibly could give you. Actually, it may have been, no, I think it might have been an MAP. The opposite of the mean is the mode, right? What's the most likely score? Well, conveniently, in a normal distribution, the mean and the mode are right on top of each other, right? So it doesn't make a difference. They're both the same data. But when we don't use CFA, for instance, if we use IRT, the mean and the mode may be different, right? We're not guaranteed to have a normal distribution. And here's the funny thing about that. This is an example. We may have a factor score distribution that looks like that. If you have a tail to it, the mean gets pulled out by the tail, and the mode is sitting here at the top. So now, so EAP factor scores, the estimate is the expected value. This is the distribution of the factor score given the data. We'll talk a little bit more about that in another slide. The standard error of the EAP factor scores is the square root of the variance function of that distribution, right? So we can quantify the mean, we can quantify the variance. It's our factor score, that's our standard error of measurement. Hooray. For MAP scores, if you're familiar with the terminology argmax, that just says take the maximum across all the F. I hope I'm using this right. I'm good with that. So here's an MAP factor score right there. Now, using likelihood theory, the maximum has an asymptotic, as you get more and more items, the variance of that estimate comes from the inverse of Fisher's information, which is the second derivative of that likelihood function evaluated at the factor score. That's what all this says right here. If that didn't make any sense to you, that's cool. Don't worry about it. This is for the REM students who, or for those of you who want to know more, and certainly my program students, right? So I didn't understand this that well either when I was in grad school for the record. But it's me trying to teach the next generation. Actually, you're like 4 generations past when I was in grad school in the 1800s. But so for our CFA model, MAP and EAP are the same. We can just focus on it. And we're going to focus on that today. When you get to IRT next year, those of you who haven't taken it yet, you're going to learn about MAP and EAP, I think. Anyway. With an infinite number of items in a non-CFA model, as items go to infinity, your estimates converge to the same, because based on likelihood theory, the large sample n of it, your estimates follow a normal distribution, and the variance shrinks to 0. And so here, because the estimate is actually the items, that's what your n counts to be. That's where it comes from. So, another interesting facet of that is if you're using a CFA model, very much like classical test theory, the variance or the reliability of a factor score is the same regardless of the factor score. Right? You give a reliability to a test. In IRT, you give a reliability to a score. It depends on the score itself. It's non-constant. So how precise you are depends on what your score happens to be. In that picture of the GRE that I showed you, you saw kind of the waning tails of it. It actually should be the opposite direction, be sort of fanning out, but it should show that the standard error of measurement changes as a function of what your score happens to be. That is why, for instance, you don't get a standard error of measurement on your GRE report. It's because if Jake, you took the GRE, and Jennifer took the GRE on the same day, and maybe got the same score, one of you would have a higher reliability. How do you like that? Well, it used to be that way. It's a little bit more standard now with the multi-stage test. It's a little bit better. All right, let me stop here. Let's take a break for 10 minutes, and we'll come back and have some fun with factor scores.